My name's Andy Layden. I'm a professor in the Physics and Astronomy department here at BGSU. I teach mostly astronomy classes, but a bit of physics as well. The field of astronomy that I study is called variable star astronomy. When you look up at the night sky, most of the stars that you see are constant in brightness, like our sun is pretty much constant in brightness. But about 1 out of 100 stars varies significantly in brightness. And the type of stars that I study, they're called RR Lyrae stars, will double their brightness over the course of about 12 hours. So imagine you're on a planet orbiting around one of these stars. Your sun would get twice as bright 2 times each day. That would make forecasting the weather a whole different kind of process. And so I've had a number of students over the years who've helped me use the Bowling Green telescope to measure the brightness changes in this class of stars. So this is the Bowling Green telescope. It's a half-meter telescope, meaning behind this part here there's a round mirror that's half a meter, about 20 inches in diameter. To give you a sense of scale, the Hubble Space Telescope is 2.4 meters, so about 5 times bigger in diameter, about 25 times more ability to catch light than our telescope. And the JWST will be, I think it's 8 meter, roughly, mirror. And so even bigger still, even bigger light bucket. The mirror is curved a little bit, so it brings the light up to the far end of the telescope and back down to the back end of the telescope. And so there's a mirror in here that can bring the light to an eyepiece, or we can move the eyepiece off to the side so that the light carries through to our CCD camera in the back. That's our digital camera that is super sensitive to light. We've also got a round filter wheel here with 8 different colored glass filters that we can automatically rotate in, a blue filter, a red filter, a green filter. And so we can isolate out different colors or wavelengths of light for our picture. And that allows us to either take an image in a certain wavelength with a certain brightness measurement, or we can combine images made with different filters, a red, a green, and a blue, to make a color RGB image. Like in most fields, astronomy has changed as technology has improved. When I was an undergraduate student, CCDs, the heart of digital cameras, were just being invented and just coming into use in astronomy. And so most of what I did was actually with photographic plates, glass plates with a photographic emulsion on them. But by the mid-1980s, early 1990s, pretty much all of astronomy had changed over to digital measurements. They're much more precise than photographic measurements. And since then, the pace of improvement in the precision that you can make with those digital detectors has improved a lot. We've put all kinds of telescopes into space. When I was in graduate school, the Hubble Space Telescope was launched. And once you're up above the Earth's atmosphere, that means you've removed one of the big sources of noise and uncertainty in your measurements. And so there have been a whole series of space-based telescopes that have made it possible to observe not only more precisely in visible light, but also to observe the stars in X-rays and gamma rays and infrared and radio waves that we can't often see from the ground. The Earth's atmosphere will block those wavelengths. I think continued advancement in digital technology will help make pictures better, help make images of the universe better, clearer, higher resolution. But the real jump is going to be when we go from the Hubble Space Telescope, which has a modest sized mirror and a modest ability to collect light, to the JWST, the Next Generation Space Telescope, which has a much larger mirror. It'll be able to collect a lot more light and see things that are fainter and farther away. And they're projecting that they may be able to see the first generation of stars that are born as the universe started to form about 13 billion years ago. And so being able to see essentially the entire visible universe is going to sort of push back the dark corners and let us see some of the things that we've speculated about but haven't been able to gain direct evidence of in the past. So it'll be an exciting time in the next 5 years or so.